All right, recording's on. Here we go. Last week we were talking about finding limits. Well, this is basically a review of chapter 1, which is limits. Want to talk about limits, so I'd like to just review some things about limits. For example, the first problem, all we do is plug in 3, and I'd get a 0 on top, I'd get a 0 on the bottom. So that means I'd have to simplify if I could. So x squared minus 2x. So if I'm going to do this problem, first thing I do is I substitute it. Substitution doesn't work. So then I'm going to factor top and bottom. So that gives me x minus 3x plus 1. These cross out, so I'm left with 1 over x plus 1. Plug in 3 now. End up with 1/4. Number 2, x over x, well, that reduces down to 1. If I simplify it down, letter A. Pretty easy problem. Now, these types of problems, like the sine of x over x squared plus 3x, they look really difficult, but what you have to understand is the sine of x over x, as the limit goes to 0, is equal to 1. And the sine of 2x over 2x is equal to 1. The sine of 3x over 3x is equal to 1. So if I can rewrite this as the sine of x over x, I've got it made. So I've got the sine of x on top. I'm going to factor out an x on the bottom, so that gives me x plus 3. Well, I know the sine of x over x is 1, so that just basically crosses itself out. So now I'm left with 1 over x plus 3. I put 0 in there, I end up with 1/3. The next problem, that one, remember the graph of this thing looks something like this. As x approaches 0, it is going to be non-existent. Good morning, or good afternoon, Caleb. How are you doing this afternoon? Then in chapter 1, we also talked about the limits as x approaches infinity, and we talked about if the function is going to infinity, then we look at the top and the highest power on top and bottom. In this problem, the highest power on top and bottom is -1 x squared over 1x squared. And so if the exponents are the same, we just take the numbers out in front. So this just becomes -1. And the next problem, the highest power on top is -x squared. Highest power on bottom is 4x squared. Take the power, the coefficients. So I end up with -1/4. So finding limits, and that basically was chapter 1. I don't want to harp too much on the limit problems because we've done enough of them. This one I want to take a little bit of time for. What is the limit as x approaches infinity of the square root of 9x squared plus 2 over 4x plus 3? What is the limit of that? That's a tough one. What's my answer? Three-fourths? I agree 100%. And the reason I agree is because it goes along with everything we've been doing. You take the highest power on top, you take the highest power on bottom. Well, the highest power on top is 9x squared. Well, the square root of 9x squared is just 3x. The highest power on bottom is 4x. Well, same powers, 3/4. That's it. It's kind of cool. I mean, when you start thinking about highest power on top, highest power on bottom, you just have to look at the 9x squared. Excellent. Today, we're going to be talking about the derivative and the tangent line, estimating derivatives, differentiability at a point, and we're going to also talk about power rules and slope of derivatives at a point. Boy, that's probably 2 or 3 weeks of AB calculus right there. However, since you guys had AB calculus already, we just keep cruising along because we have to get all of this stuff done before we start with the newer stuff. All right, so now when you get into Khan Academy, you go to differentiation, definition of basic derivative rules. And so this is what it should look like. Defining average and instantaneous rates of change at a point. That is, average rate of change is f of b minus f of a over b minus a, which is really slope. That is what we're dealing with. When we deal with derivatives, we're really trying to deal with the slope at any given point. Now, we're going to go at this a little bit slower, but that is what it is. It's slope. So I'm going to, I wish I had a clean sheet of paper here. Okay, so if I gave you, and let's review a little bit from last year because we already know how to take derivatives, right? If I gave you y is equal to x squared, and I said that I wanted to know what the slope, the instantaneous rate of change is. Instantaneous. No. Let's say I wanted to know what the average rate of change from, let's go 0 to 3. And then I want to know what the instantaneous rate of change at x equals 2. Okay? So those are the two things that really starts off with derivatives. Okay? What is the average rate of change from 0 to 3? Okay, can anybody tell me? Average is 2, instantaneous is 4. Okay. So to find the average rate of change, what we have to do is we have to find f of 0. Well, if I plug that in here, 0 squared is 0. F of 3, which would be 3 squared, which is 9. So then I'd have to find the average rate between these. And remember, to find the average rate, it's really the slope. So it's really 9 minus 0 over 3 minus 0, which is 9 over 3. Well, I don't agree, Caleb, with your average rate of change between 0 and 3. I think the average rate of change is 3. Caleb, does that make sense? I'm not sure how you found your average rate of change. Oh, no, no. Average rate of change, if I drew this out, here is my parabola, and the average rate of change, so at 0, the point is right here, and at 3, the point is up here, so this point here is 0, 0. And this point here is 3, 9. The average rate of change is, if I drew this line, what is the slope of that line? That is the average rate of change. All right? So the average rate of change there should be 3. And the instantaneous rate of change is when you take the derivative of this is 2x. And if I put 2 in there, I do get 4. So the instantaneous rate of change is 4. All right, Henry, any question on average rate of change and instantaneous rate of change? Do you understand how we came up with the instantaneous rate of change? Okay. And the average rate of change? You good on that one too? Okay. So there's a huge difference between average rate of change and instantaneous rate of change. And since we understand how to find derivatives, we don't have to talk about, you know, the old way of taking derivatives, because last year I remember teaching you guys, this is how we found the derivative of a function. And I'll go through a problem, okay? So for example, and we found it at a point and finding the derivative. So let's say I wanted to find f prime of 2, and I was going to use this. I'm going to use the definition of a derivative. Then I would have to do the limit as h approaches 0, and f of, so this would be f of, and I'm using f of x equals x squared. Okay, so we know that. So we're using x squared. So if I was going to do this, I would do f of 2 plus h minus f of 2 all over h. And then I plug this into my function, right? Because 2 plus h, if I plug that in there, that would be 2 plus h squared. Well, 2 plus h squared is 2 plus h times 2 plus h, which gives me 4 plus, what is that, 4h plus h squared. Okay, so that goes right here. I'm going to put that in there. So that's 4 plus 4h plus h squared minus f2. Well, if I put 2 in there, that's 4, isn't it? All over h. Well, that 4 and this 4 crosses out. I've got 4h plus h squared over h, so I'm going to factor out an h. So that gives me 4 plus h over h, crosses out. And this is the limit as h approaches 0. So if I put a 0 in for h, lo and behold, I get the limit of 4, or the derivative of 4. And we knew that because we know how to take derivatives. However, this is, in the olden days, this is how we found the limit at any given point. And man, I can tell you, it was beastly when you ended up with functions like, if I gave you a function like f of x, or f of x equals like x to the third plus 2x, whew, this would take all day, because then you have to plug this into here. 2 plus h to the third power plus 2 plus 2. Oh, it was brutal. So we don't usually use this anymore because we know how to take derivatives without it. But this is the definition of a derivative right here. Okay. The derivative using the definition. Okay, so if I had, it says find the derivative of f of x equals when f of x equals f of x squared. Okay, so you plug this in, blah blah blah. You get all the way down here, and you get the derivative of 8x. Well, guess what? We already know that if this is f of x, the derivative of that, we bring the 2 down, we just have 8x. Way easier than doing all of this work. Okay, so hopefully you guys still know how to take derivatives, because if not, we could go back and use the definition and find derivatives that way, but oof, I don't want to do that. That is painstakingly hard. Okay, the notation for a derivative, we can use y prime, we can use dy over dx, we can use df over dx, we could use d dx f of x. Usually we just use y prime or dy dx. These are the two that we use most of the time. The derivative at a point, and I just did this problem here. If we used, if I wanted to find the derivative at a point, I can use this formula, f of x minus f of a over x minus a. The limit as x approaches a. Or you could use the other one as the limit as x approaches, or x approaches h. It's the same thing. It is the very same thing. Now, finding a tangent line is very important in calculus. Being able to find a tangent line at any given point. So I'm gonna ask you guys to find an equation of a tangent line at x equals 3. Okay? So I want you guys, both of you, to find the equation of this tangent line at x equals -3. I just want to make sure that you guys know how to find an equation of a tangent line. Okay? So go and see. I want to just see if you guys still remember how to find an equation at a tangent line. Okay. What is, now, an equation of a tangent line is not a number. -6 is a number. It is not an equation of a tangent line. Okay. I want to know what the equation of this blue line, what the equation of the tangent line is. Okay. Caleb, you had me last year, correct? What two pieces of information do you need in order to write an equation of a tangent line?
The slope and y-intercept.
That's the first thing you should be writing down on your piece of paper. Okay. What are the two pieces of information you need in order to write an equation of a tangent line? Slope and y-intercept. Disagree with you. Okay. That is not correct. Point and slope. Anytime I ask you this year to write an equation of a tangent line, the first two things that you should put on your paper is point and slope. Well, how do we find these? Well, point, okay, so this is going to be -3 comma, well, here's my equation, so -3 squared is 9. So there's my point that's on the line. So I have my point, -3 comma 9. Now, how do I find my slope? Well, we have to take the derivative. We got to plug -3 in there. You guys already said that the slope is -6, right? But that is not the equation. Now we have enough information to write my equation. We always, in this class, in calculus, we always, let me repeat that, we always write our equations in point-slope form. Point-slope form, point-slope form. What is point-slope form? Point-slope form is y minus y1 is equal to slope x minus x1. That is point-slope form. So what do I have to fill in? Well, you have to fill in your point. This is my point. That's your point. And this is my slope. If I'm going to write my equation, y minus 9, thank you. Y minus 9 is equal to -6x plus 3. That is how we write equations in this class. We write them in point-slope form. Why? Because it's so much easier than write them in slope-intercept form. How are you going to find the y-intercept of this line? I mean, you could, if you took your time, you could find it. But point-slope form, you can find the point on there. You should be able to find the slope using a derivative. We always use point-slope form in order to write an equation of a tangent line in calculus. Henry, you remember point-slope form of a line? All right. So every equation that I ask you to write this year, unless it specifically says write it in slope-intercept form, you're going to write it in point-slope form because it's so much easier. It saves time. It saves lots of time. Now, if I asked you to write the equation of the tangent line in slope-intercept form, guess what? I would still do it in point-slope form, and then I would just rewrite it. Now I have it in point-slope form. Now, if I wanted to write it in slope-intercept form, I would just multiply through here. So I'd have y minus 9 is equal to -6x minus 18. And then I would add 9. I'd bring that 9 over here. So I have y is equal to -6x minus 9. What is the y-intercept of that graph? Okay. Where does that graph cross the y-axis? Now that I rewrote the problem in slope-intercept form, you should be able to look at that equation and say, hey, the y-intercept's -9. So this graph is not going to cross the y-axis until way down here at -9. Okay? So I should be able to ask you to write something in point or in slope-intercept form. Now, if I ask you to write something in slope-intercept form, the first thing you should do is really write it in point-slope form and then change it up. Okay, that is the easiest way of doing it. Okay, I think we just, all right. So here, it says write an equation of a tangent line to x squared at x equals 2. I want you to write it in point-slope form, and I want you to write it in y-intercept form. Okay, so I want you guys to write an equation for a tangent line. So my tangent line is x equals 2. Tangent line would look something like this. Okay, so the green line, I want you to write an equation of this green line in point-slope form and y-intercept form. All right, go ahead, because this is so important. You got to spend a little bit of time on that. Caleb, can you fill in point and slope up there on the slide? Because that's the first two things that you want to find, right? Point and slope. So what is your point? What is your slope? Two, 4 is correct. Why is it 2, 4? Because I already told you that the x value is 2. So in order to find the y value, we just plug it back into our equation. 2 squared is 4. So I've got my point. The slope, I just take the derivative of this. That's 2x. Plug 2 in there. 2 times 2 is 4. So my slope is 4. So I know that the slope of this green line is 4. I know the point is 2, 4. So the equation in point-slope form is y minus 4 is equal to 4x minus 2. Excellent. So that y minus 4 equals 4x minus 2. Now, in order to rewrite it in slope-intercept form, okay, you both have 4x minus 4. I like it. Very nice. Excellent. That is a big portion of what we do first semester, being able to write equations of lines in point-slope form or slope-intercept form. Excellent. Nice job. Okay. I guess we don't really have to do this stuff here. This is just stuff that on there. Now, when might a derivative fail to exist? A derivative will never exist at a corner. Can somebody tell me why? Why couldn't there be a derivative at a corner? Okay. Why couldn't there be? It does have slope. Well, okay, I agree with you, because you don't know what the slope is. I mean, look at this slope, looks like it's positive 1 here, it looks like it's negative 1 here. How do you know what this slope is? Is it negative 1? Is it positive 1? So you can never take a derivative at a corner. You can never take a derivative at a cusp. Same reason. How do you know what slope to use? Do you use this slope? Do you use this slope? It doesn't have a slope there. So you can't take it at a corner, at a cusp, at a vertical tangent line, because a vertical line would be undefined, and where there's a jump. So there's 4 places you cannot take a derivative: a corner, a cusp, a vertical tangent, and where there's a jump in the graph. Right? Those are places you cannot take derivatives. Now you can take a derivative anywhere else on that graph, just not at those points. Okay. Rate of change. All right, we have seen how the derivative is used to determine slope. The derivative can also be used to determine the rate of change of one variable with respect to the other. Applications involving rates of change occur in a wide variety of fields: population, growth rates, so many different things. And then we go velocity and acceleration. So rates of change, we're always going to be using rates of change this year. All right, average velocity. This is important, okay? Average velocity is the change in distance over the change in time. Change in distance over the change in time. Instantaneous rate of change is the rate at any particular moment, okay? It's instantaneous. So there's 2 different, the average velocity, okay, change in distance, change in time, instantaneous rate of change, which is basically instantaneous velocity. So here's a problem that we could do. It says a billiard ball is dropped from a height of 100 feet. The ball's height at time t is the position s equals negative 16t squared plus 100, where s is measured in feet and t is measured in seconds. Find the average velocity over the following time interval. So we're finding the average velocity. And again, average velocity, whoops, is the change in distance over the change in time. I'm going the wrong direction. Okay, so the average distance, so from 1, so I'm going to go f of 1, f of 2, that's going to give me, so f of 1 is, if I put 1 in here, 1 squared is 1, negative 16 plus, that's, I believe that's 84. And if I put 2 in here, 2 squared is 4, negative 16 times 4, and now I'm going to get my calculator out. So negative 16 times 4 plus 100 is equal to 36. All right, so the distance it's traveled is right here. The time is 1 second, isn't it? Because I'm going from 1 to 2. So average velocity, 84 minus 36, is going to be 48. Change in time is just 1 second. So the average velocity of this ball is 48 feet per second. That's it. That is how we find average velocity. Now, if I wanted to find instantaneous velocity at, let's say, 2 seconds. 2 seconds. I want to know what the instantaneous velocity is. Well, then I would take the derivative of it. That would be negative 32t. So put 2 in there. That would be 64 feet per second, wouldn't it? So there's a huge difference between average velocity and instantaneous velocity. A huge difference there. Average velocity, time over, and what did this really turn out to be? Isn't that slope? When you think about it, that you just go 84 minus 36 over 1 minus 2. It's basically slope is average velocity. And then we could also do limits, and we don't want to do that because it takes forever and a day. Okay, so we don't want to do that part. Okay, now the second part today is find the derivative of a function using constant rule, power rule. These are all rules that you should know already. All right, so constant rule. The constant rule says we have used the limit definition to find derivatives. In this section, we will be introduced to several differential rules that allow us to find derivatives without direct use of limits definition. So this is how we find the limits no matter what. The constant rule. The derivative of a constant function is 0. That is, if c is a real number, then the derivative of c is 0. Okay? Not real difficult. Just remember when we did derivatives, we had like 3x squared plus 4, we would take, so this would be 6x plus 0. The derivative of any constant is 0. Okay? And doesn't that make sense? I mean, if you have, let's say we had y is equal to 4. That's a constant, right? Y is equal to 4 is a horizontal line at 4. What is a derivative? A derivative is the slope at any given point. Well, the derivative or the slope of a horizontal line is always 0. So that makes sense why that is always going to be 0. So using the constant rule, what is the derivative of y is equal to 7? 0. F of x equals 0. Negative 3, 0. Now, last year, when you were in AB calculus, you probably had some problems with these. Not really. Hopefully you didn't have problems with the constant rule. Now the power rule. The power rule says if you have 3x to the 4th power, you multiply the power times the coefficient. So 4 times 3 is 12, x, and then you subtract 1 from the power. So the derivative of 3x to the 4th is 12x to the 3rd. That is the power rule. Here is the rule for power rule. Power rule says that if taking the derivative of x to the n, your answer is nx n minus 1. It's kind of weird when you see it written out. It's so much more confusing than just to look at an example. So what are these derivatives? Okay. Caleb or Henry, give me the answers to all three of these. 3x squared. All right, I agree with that. Okay. Uh-oh, you guys are slowing down for the next one. What is the derivative of the third root of x? 1/3 x. Now, 1/3 x to the negative 2/3. Okay, so if I was going to take the derivative of this, the first thing I do is I just rewrite it. That's the same. The third root of x is the same thing as x to the 1/3. So I bring the 1/3 down. So I've got 1/3 x. Subtract 1 from here, and that's negative 2/3. That is my derivative. And the last one, negative 2x to the negative third power. Okay, now I don't know, but I would rewrite this as x to the negative second power because I can bring that to the top. Now, if I bring the negative 2 down, that gives me negative 2x. Subtract 1 from that. Caleb, you still know how to use the power rule. Very nice. Excellent. Oh, Henry, you've got the answers too. 3x, 3x to the third. Get rid of that third and put a 2 there. I'd agree with that. And then the other two, Henry, I agree with. But not the 3x to the third. That should be 3x to the second. You're probably trying to type in too fast. So Caleb didn't get it first. The constant multiple rule. Constant multiple rule says that if you have a constant number in front of the derivative or in front of the function. So for example, if I had 4x squared, okay? That 4 in front, I don't even have to deal with it. I could just leave it out in front and then bring the 2 down. So that would be 2x to the first. And then I would just multiply the 4 times 2, which is 8x to the first. But nobody does that. Everybody just takes the 2 and multiply it by the 4 and get 8x to the first. So that constant multiple rule, yeah, I'm not real sure I'd use it. I mean, I wouldn't move that 4 to the outside. It makes no sense to do that. Just easier just to multiply the 2 times the 4 and do it that way. However, when we have, for example, if we have 3 sine of x, it comes in a little bit handy. It just says that we can take the derivative of sine of x and just leave the 3. So this would be 3 cosine of x, wouldn't it? So the constant multiple rule does help when we're dealing with cosines. Or if I had, let's say I had 3e to the x. Caleb, you still know what 3e to the x, the derivative of 3e to the x would be? Just checking to see how. It would be 3e to the x. Henry, very nice. You guys remember your derivatives. That's going to make, if you guys remember your derivatives, this section, this chapter is going to go really well for you because basically what we're doing is we're just reviewing all the derivatives from last year. Okay, that's it. The sum and difference rule. The sum and difference rule just says that you can break functions down. So for example, if I had f of x is equal to, let's say, 2x squared plus 3 cosine of x minus e to the x. Okay, it just says that I can take the derivative of this, and then I can take the derivative of this, and then I can take the derivative of this. That's all it's saying is you can break the derivatives apart. So what would my answer be here? It'd be 4x plus cosine is negative sine, isn't it? So that'd be negative 3 sine of x minus e to the x. So that would be my derivative. I can take them all separately. I don't have to look at the whole thing and say, whoa, that's a crazy function. No, you just take the derivative of each separate piece. That's it. Whew. I really talked fast today. I looked at my slides and it was like, man, I had 41 slides to get through today and we're already done. Now, Caleb, nope, I'm gonna before I let you guys go. Caleb, did you get my email yesterday about signing up for the College Board site? Oh, you made an account. Okay. So what I'm going to do is I'm going to just share my screen for a second, okay, with you guys. And I'm going to, oops, I wanted to share my screen. That didn't work too well. What the heck? I don't want to add. Let me jump out of here. Let me jump back here. Okay, so I'm going to share my screen here. Okay, I'm going to go to the College Board. Let's see here. Where is that? All right. Do you guys see my screen? I'm just jumping into the College Board right now. Can you guys see that? I'm hoping you can, because I can't see your thing. All right, so I got to remember what my password is, because my password is different on everything. All right, let me see here. So I'm going to jump in. Here's my password. Okay, so all right, let's see if that's right. All right, so I'm in the College Board, so this is what you guys should see. But you guys should see I have two classes. I have AB and BC here. So you guys should see this. Now, what is so cool, I think, so we just finished Unit 1, right? Unit 1 was limits and continuity. You can practice. Now, these problems are pretty tough. I will say that. There's some pretty tough ones in here. So let me go here, unlock. And you can see that it takes a while. Please wait a while. Okay, so here's some problems. If I click on that, they have some problems to get you ready for the AP test. For example, here it says if f is a function defined by f of x equals 1 minus, or x minus 1 over 1 minus 1 over x, the limit as x approaches 1 is equivalent to which of the following? Oh boy, if you put 1 in here, you get 0 here. Put 1 in here, you get 0 here. Oh boy, how do I solve that thing? So there's some really good problems. Now, we know L'Hopital's rule says that we can take the limit of the top over the limit of the bottom. So and it just says, which is equivalent to the following? Well, the limit as x approaches 1 of x minus 1 over, I'm going with D. Now, can I check myself? Does it show if it's right or wrong? Because I haven't really dealt with these yet. So, and then so there's all these different types of problems. And what I'm going to do is let's go to the scoring guide. This may take up to 30 seconds. I only did one problem, so it really shouldn't take that long. But there's some really good problems here. And this is what I'm going to assign some of these to our class. That's why I want everybody to sign up, because I can go in here and I can assign anything I want to you guys, which is cool. And then it's pretty cool. So I've just been playing around with it. It looks pretty cool. It looks like it's got some really cool stuff in there. So if you guys want to play, you absolutely can play around with it. I think there's a lot of cool stuff in there. And I will be using some of that in the near future. So thank you guys for signing up. Or I know, Caleb, you said you signed up. Henry, you said you were going to sign up. So hopefully we get everybody signed up, and then we can start using some of the problems out of there. That is all I have for you guys today. Any questions? All right, see you, Caleb. See you, Henry. Have a great week.